the determinant. Find the determinant of that matrix. Recall what we define the determinant to be. That this is the difference in the elements of the main diagonal from those of the other diagonal. You have a matrix A divided this way. You can define as this or that A. This is the by 2 will give us 6 minus the element by 5, which is 5, and this will give you 1. So the determinant of this matrix is 1. But what we do next? That if the determinant is 1, then this matrix has an inverse. We need to note at this point that if we find that the determinant of the matrix A is equal to 0, how do we interpret that? There are two interpretations that if the determinant of the matrix is 0, then we call that one a singular matrix. So a singular matrix is that matrix that has a determinant equal to 0. Meaning that this is a matrix that is defining the same equation. Like if you have an equation, 2a plus 3b is equal to 5. Then I have 6a plus 9b is equal to 10. We are defining the same equation because 2 like equation 1. This is a product equation 2 is twice equation 1. So we define the same. So as we get the standard of 2, 3, 6, 9, that determinant will be 2 by 18 minus 3 by 6 is 18. That gives you 0. So we will define the same equation. Geometrically, this defines the same equation of the line. If you put the line 2m plus 3b is 5. Then put the line 6m plus 9b is 10. You can this is the same line. We are dividing the same line. And therefore, matrices with the determinant are 0. Which we are dividing as the matrices are those matrices that do not have an inverse. So the determinant is 0, and therefore there are two inverse. And hence we cannot see the value. There's step 2 in finding the inverse of a matrix. The first result is the determinant. If the determinant is 0, this like matrix has no inverse and it's only a single matrix. Now, number 2 is that we interchange the elements in the middle diagonal and divide the size of the elements in the other diagonal. That this is our middle diagonal. We interchange that like this. So that it will be 2. Divide the element of the size in the other diagonal. This is the 1. So it will be negative 1 as we are seeing in B. The interchange in B is 3, 2. We divide the size in 1, negative 1, 5, negative 5. Then the last number 2 is now by getting the difference of 1 over the standard times the matrix contained in 2. So the matrix that we are obtaining is the 2. Remember, we are bound to the standard is 1. So the recipient of that inverse of that determinant times what we get into 2 will give us therefore inverse of that. And not only that, this is as far as multiplying the matrix. It should not be the other way around. That the scalar must always multiply before the scalar ratio. Let us use that to find the inverse of the following the matrices. Consider the matrix A defined as 2, 3, minus 4, 5. Step 1, evaluate the determinant of A. The determinant of A will be 2 times 5 minus 3 times negative 4. So this will give you 10 minus negative 12, and that will give you 22. So the determinant is 22, and this is not equal to 0. Therefore, this matrix is not a single matrix. Hence, it has an index. For step 2, we revise the sign. We revise the sign and have the matrix. To an extent that we can move the index to the inverse. Much they have to be equal to. The reciprocal of the determinant 1/22 times. Now we can check the elements in the middle now. These 2 parts will give us 5, 2. Remind the sign of the elements in that determinant. This is positive 3, so it will be negative 3. That will be 4, and that will be 4. So if you have this kind of multiplication, this will give you the inverse at 5/22, negative 3/22, 4/22, and then 2/22. And this is what we are finding for the inverse. So we can easily prove that there is A inverse. This will give us an identity. This generalization. A inverse will be equal to X plus A, and this will be equal to the identity. Once that is proved, then A inverse is defined as given. We will have other examples which we may refer. But of importance now, let us see how can we use this to solve linear equations. That we can apply this as matrices so that we can use them to solve linear equations. How is this done? In general, given a system of linear equations that have 2 unknowns, the 2 equations, then we can apply matrices to solve that. Look at the equations. Ax plus bx is equal to s. Bx plus dx is y, sorry. This is equal to g. From this system of equations, we can generate 3 sets of matrices. Look at this. These are elements in x, these are elements in y, and these are constants. We can write in matrix form as coefficient of x is n, and the second one coefficient of x is b. In one, the coefficient has x in one. Well, the coefficient has x. But how do I get the equation? I cannot put x and y in one form, so that if I look by x, I get x, if by y, I get y. So this is the left hand side in the equation form, the matrix form. This is what we do as T. In matrix algebra, we refer to this as the matrix of cohesion. We refer to this as the matrix of unknown. And we have this as the constant, the matrix of constant. So, given any system of linear equations, we can extract the matrix of coefficients, the matrix of unknowns, and the matrix of constants. We now know that a matrix multiplied by this inverse is the identity. We need to devise a way of considering tasks so that this is the identity. An identity that will leave only the unknowns. And whatever we look to the left hand side, will be the right hand side. So we must consider the left hand side. Because what and because A inverse is equal to A inverse that is the relation. So if we do that, there will be the notes and the constant that give us the result or the result will be of the direction. So consider the example that we have. That we have and suppose we use that to solve the equation if x plus y is 7, 5x plus 2y is equal to 12. This is the set of matrix. So let us extract the matrix equation. That's the matrix of coefficients. The coefficients for x are 3, 5. The coefficient of y are 1, 2. The constants here are x and y in column form, and the constants are 7 and 12. So this is the matrix equation. Consider the coefficient matrix. We need to get the determinant of this. So the determinant of this 3, 1, 5, 2, 5. If I read this way, remember how we got the determinant? This is equal to the determinant of 1 by 5, and this is equal to 6 minus 5, and that is equal to 1. And therefore, the impact will be equal to already I have 1. Now, the coefficient matrix, I can take them to the example and having as 2, 3. Reverse the elements. Number 2. Reverse the 1. That is 1 is 5, that is 5. And therefore, the inverse will be equal to 2 negative 1 5. Now back to our question. This one. We have how many of the inverse matrix. So when you use that, you have the inverse by the whole set to have the inverse as 2 negative 1 negative 5 to be by the left hand side 3 1 5 2 x y, and this will be equal to, we are starting with the inverse so that the right hand side is compatible. So the inverse is 2 negative 1 negative 5 3 by the constants 7 negative 1. So what are these? Then what are these? What are that? Then we see what we have. You can share your results on the chat box. On the chat box. Check that this product will give you 1 0 0 1. They are not xy. This will be equal to 2 by 7 is 14 plus minus 1 by x squared. 14 minus 12 that gives me 2. Negative 5 7 is negative 35. Right. 3 by 12 is 36. So minus 6 and you want 1. So if you want 1 by x plus 2 by 1 and give you x. Plus 1 by 1 and give you 1. So this one gives you 1. Remember how to find equal matrices. Two matrices of the same order are said to be equal if they have the corresponding parameters equal. So this x1 is 1 and then x will be equal to 2 and y will be equal to 1. That is the solution to that matrix. That is the solution to that matrix. Try the following. For example, 2. Find the inverse of 2, 3, negative 4, 5, and hence solve 2x plus 3y is equal to 86. Minus 4x plus 5y is equal to 1, 4. Find out that, then let's see what it happens. Find out that, then it should be. You want to chat box here. This is 1. Proceed to solve that. They will not be with the time. You must cover.
X is 44, Y is 66. Wengine watapelekwa kama gari ya Meru. They bring in the grammars.
I've seen most of you are giving the answer as X is 44 and Y is 66. X is 44, Y is 66. Hope you've done the correct computation. Let us now look at an alternative way of solving such matrices, solutions to linear equations, and this by what is referred as the Cramer's rule. That's by inversion. Next, we look at the Cramer's rule. The alternative way of finding the solutions is by the application of the determinants only. And if you use determinants only, this is what is referred as the Cramer's rule. What is it that Cramer's rule is all about? Cramer's rule gives us the solution by getting the quotient of the respective determinants by replacing the coefficients by the constants. Recall, we said that if I have x plus by is s, and I have dx plus dy is t, then the system of matrix equations, the coefficients are a, b, c, d. Their norms are x, y, and the constants are st. So by Cramer's rule, we replace, if we are solving for x, we replace the coefficients of x by the constants. If we are solving for y, we replace the coefficients of y by the constants. How is this done? We want to get a solution for y. For x, let's start with this. For writing the solution of x, we need to get the determinant of. If I replace the coefficients of x by the constants, the coefficient matrix will turn to ST. Those of y will remain B, D. So we get that determinant divided by the determinant of the coefficient matrix A, B, C, D. If I do this, this means determinant. And similarly for y, we are solving for y, therefore we replace the coefficients of y. I want to be very slow. We replace the coefficients of y by the constants to have those of x, A, C remain, those of y now change to ST with upon replacement divided by the coefficient, the determinant of the coefficient matrix A, B, C, D. That is what Cramer's rule is all about in simple terms. We are getting quotients of determinants. That for x, we substitute the coefficient matrix with the constants. For y, we substitute the coefficients of y by the constants. Then we get the respective quotients, and that gives us the solution. Look at our example 1. From this example, 3x plus y is equals to 7. 5x plus 2y is equals to 12. We generated the matrix equations as 3, 1, 5, 2, x, y. This was 7, 12. So if we want to solve for x, we want to solve for x, which means we substitute the coefficient of x by the constant. This will give us 7, 12. Then those of y remain 1, 2. Divided by the determinant of the coefficient matrix, 5. This is 3, 1, 5, 2. This will be equal to, let us find this determinant, this 2 by 2. 7 by 2, that gives us 14 minus 1 by 12, that gives us 12. Divided by 3 by 2 is 6 minus 5 by 1, that's 5. And this gives us 2 all over 1, and that gives you 2 as the answer. So x is 2. Then we do the same for y. For y now, we substitute the coefficients of y by the constant. So those of x remain, the x are 3, 5. Those of y become 7, 12. That determinant divided by the determinant of the coefficients, 3, 1, 5, 2. This gives us 3 by 12, that's 36, minus 7 by 5, 35, divided by the determinant of the coefficient matrix, 3 by 2, 6, minus 1 by 5, 5. And this will give you 1 over 1, and that gives you 1. So x is 2 by Cramer's rule, y is 1. That is the simplest way. Look at example 2. From example 2, we can extract the system of matrix equations as 2, 3, minus 4, 5. X, y. This will give you 286, 154. So let us solve for x. This will be equal to, then solve for y. Using now the Cramer's rule. Solve using Cramer's rule. We are doing 5. After 2 by 2 is now 3 by 3. Then we conclude matrix algebra. Internet is drop.
Progress.
So if we follow the same process, for x, this will be equal to the determinant of 286, 154, 3, 5, all over 2, 3, negative 4, 5. And this gives you 286 by 5, that is 30. 40 plus 3, 43. 10 plus 4, 14. Minus 3 by 1, 54. That's 12, 15, 16, 3, 4. Divided by this 10 minus 12. So this will be equal to 1430 minus 462. This is 8, 12, 6, 13, minus 7, minus 4. That is 9. 968 all over 22. And this gives you 44. For y, we substitute for y coefficients. So for x remain 2, negative 4, then 286, 154, divided by the coefficient, determinant of the coefficient matrix, 2, 3, negative 4, 5. This will be equal to 2 by 154, that gives you 8, that's 10, that's 2, 3, minus this minus this minus 4 by 6, that's 24, carry 2, 32 plus 2, 34, then 8, 11, divided by. The denominator is 10 minus negative 12. So 11, 44 minus 308, that is 14.
Is it minus?
Which one? Yeah, this minus. Because this will give you negative. So we add the 2. This is 12. 5, 4, 1. So this gives you 14, 52 divided by 22. And that should give you 66. That should give you 66. So this is how we can go about as an alternative. The first was by inversion. The second is by Cramer's rule for 2 by 2, meaning we have 2 equations with the 2 unknowns. 2 equations with the 2 unknowns. So correct if you didn't get that. So I see a number of you had gotten it correctly. So finally, let us look at the 3 by 3 matrices. Finally, we look at 3 by 3 matrices. So 3 by 3 matrices, these are matrices that have 3 rows and 3 columns. They have 3 rows and 3 columns. We did see for 2 by 2 how to get the determinants. We need also to redefine how do we go about it for 3 by 3 matrices. Now, for us to get the determinant of a 3 by 3 matrix, there are 2 methods that we can use. One is that we need to reduce the 3 by 3 to 2 by 2 by deleting appropriately the relevant row and column to reduce it to 2 by 2 and then proceed with the process. I repeat that we reduce the 3 by 3 to 2 by 2 by deleting the appropriate row and column and then evaluating to get the determinant. How is this done? For 3 by 3 matrices, suppose you have a matrix A defined as A, B, C, D, E, F, G, H, I. Then what we are saying is that the determinant of A is obtained by reducing this to 2 by 2. How do we reduce? We can reduce by using row 1, row 2, or row 3. Any of those will give us the same result. But how is this done? I want to adopt row 1 with the elements A, B, C. That if I want to reduce from the first element in row 1, column 1 is A. So if I delete row 1, column 1, A is common. What will be the 2 by 2 that I'll be left with? We are deleting row 1, column 1 to leave us with E, F, H, I. This is the reduced 2 by 2. Now, we must be cautious because as we use row 1, we must make some conventional assumptions. For row 1, the first term would be positive, the second negative, the third positive. We are interchanging plus, minus, plus. For row 2, we interchange for minus, plus, minus. Row 3 is plus, minus, plus. So this sequence of signs has to be observed. So if you are using row 1, then we are taking the sequence of signs plus, minus, plus. If you use row 2, the first term will take negative, then plus, then negative. So we are using row 1, so this will be positive. The second term, we negate. So we are deleting second, row 1, column 2. So the common term there is B. So it's row 1, column 2. If I delete those ones, I'm left with D, F. Because this is deleted and this. What are we left with? It's DF, then GI. We are performing the reduction. Then the third term is plus. The common term in row 1, column 3 is C. If I delete row 1, column C, I'm deleting row 1, column C, I'll be left with this, which is D, E, G, H. So if I evaluate A times this determinant minus B times this determinant plus C times this determinant, what I get is the determinant of A, which is 3 by 3. Let us look at example. Example. Consider the matrix A defined as 2, -3, 4, -1, 2, 4, 3, -3, 1. We want to get the determinant of that. This is 3 by 3. So that A will be equal. We reduce the first term 2 by 2 using row 1. This row 1, column 1, the common term is 2. The reduced 2 by 2, if I delete row 1, column 1, I'll be left with this. This is 2, 4, -3, 1. Minus. The second term on row 2 is -3. So we are deleting row 2, column 2. To leave us, we are deleting row 2, column 2. That leaves us with -1, 4, 3, 1. Then plus. Look at now the third term. The common term is, we are on row 1, the third term is 4. So 4 lies on row 1, column 3. So if I did row 1, column 3, I'm left with -1, 2, then 3, 1. I repeat, we want to get the determinant of matrix A, which is 3 by 3. That by reduction, we shall be deleting the relevant row and column. So if we use row 1, the first term is 2. Deleting row 1, column 1 leaves us with 2, 4, -3, 1. Then reduce 2 by 2. Minus, because we are following the sequence of signs for row 1. That for row 2, the common term is -3. So if I admit row 2, column 2, I'll be left with -1, 4, 3, 1. That's what I have. I'll reduce 2 by 2. Plus, the third term is positive. So I have the plus, and the common term is 4. So if I did row 1, column 3, I've deleted all this. I'll be left with -1, 2, 3, -3. Did I error somewhere? Yes. It is row 1, column 3, -1, 2, 3. This should be -3. So we evaluate this determinant. How do we do that? This would be equal to 2 times 2 by 1 is 2 minus 4 by -3 is -12 minus -3. We are here. -1 by 1 is -1 minus 4 by 3 is 12 plus 4. -1 by -3 is 3 minus 2 by 3 is 6. So if we evaluate this, we have 2 by 2 minus 12, that's 14. Minus 1 minus 12, this gives us -13. -13 times -3, that gives you 39. This will be -3 times -13. If we have to go stepwise, plus 4, 3 minus 6, that gives you -3. So evaluating this, we have 2 by 14, that gives you 28. -13 by this, that gives you 39. So the negative remains, plus 4 by -3, that gives you -12. So evaluate this, 28 minus 39 plus -12. So that's 39 plus 12, 11, 5, 6, minus 28, 3, 5, 3. So this should give you -33. That should give you -33. So -33 is the determinant. This is by row reduction.
Students are saying it's -23.
Negative?
23.
-23. Now this gives us -23, yeah. Negative 23 sorted. So we can do one more example. Then watafutia hapa example moja. Find the determinant of the following. Say matrix B defined as 3, 2, 2, 2, 1, 2, 1, 0, 1. Find determinant B using the same process. Find the determinant of B using the same process. That is negative 23. So it's good that they are following and they're also working it out. That one should be, oh, it's minus. It's 28 minus 39 minus 12. Unapotea kama internet yangu. Oh. Wagonapata. The answer should be 1.
Wow, umepata.
So if you have worked out correctly, this gives you 1. The determinant is 1. Now that is method 1. How about method 2? That we can also find the determinant of a matrix by just modifying the matrix that we have, so that instead of it having been a square matrix, we make it a rectangular matrix by adding the first 2 columns. Look at the first case. We had matrix A defined as 2, -3, 4, -1, 2, 4, then 3, -3, 1. This is a square matrix that we can modify this to a rectangular matrix and then proceed to compute as follows. That the determinant of A will be given by, we have this A matrix as 2, -3, 4, -1, 2, 4, then 3, -3, 1. So how can I make this a rectangular matrix? I add the first 2 columns, 3, -3, then -1, 2, then 3, -3. Then look at it clearly, that I can now get this a 3 by 3 matrix. I can look for those that will form 3 values, so that I have that as 1, 2, 3. Remember, this is negative. So if I get these products, 2 by 2 by 1, that gives me 2. -3 by 4, -12. -12 by 3, -36. Then 4 by -1 is -4. By -3, that gives us 12. Look at those that are written in blue. Then I want to show the reverse in terms of the red color. Which one gives me 3? You see, I've used the blue for the positives and the red for the negatives. How does this work? That is -3 by -1, that's 3 by 1, that gives you 3. 3 by 4 by -3, this is 12. 12 by -3, that gives you -36. Then 4 by 2 by 3, that gives you 8, then 24. Now what do I do? Get those that are moving down, the sum of this minus the sum of this. So it's 2 plus -36 plus 12. Then 24 minus 36 minus 3. Then get the difference. I repeat. Get the sum of those products in blue minus the sum of the products in 3. Then let us see what you get and compare with what we had. Do the same for matrix B using this approach. This value we got it wrong. This was 2. Please correct this value. In the first column with 2, negative 1, 3. 2, negative 1, 3. So this should be 2. Please correct, this is 2. So that when you multiply this 8, and this will give you 24. Wow. That will give you the same results. Now this as we wind up, this is going to be the most complex for them.
Let me send you something on WhatsApp. Let me send you something on WhatsApp.
Let us now look at the inverse of 3 by 3. Let us look at the inverse of 3 by 3. Now, the following procedure is followed. And as we have been looking at it, procedure number 1 is to evaluate the determinant. Evaluate the determinant. So we have seen how to evaluate the determinant of a 3 by 3 matrix. So if the determinant is 0, then the matrix is referred to as a singular matrix, and therefore it has no inverse, as we saw under 2 by 2 matrices. So the first step, always find the inverse. If the inverse is 0, then that matrix has no inverse. You don't proceed. Then number 2, step 2, if the determinant is not equal to 0, then you proceed to number 2. Define the matrix of minus. The matrix of minus. What is this matrix of minus? This is a matrix obtained by reducing and replacing each and every element of the matrix by the determinant of its reduced 2 by 2. What do I mean? That we must reduce each element. We must reduce and find the determinant for after reducing each element to 2 by 2. Suppose I have the matrix A, B, C. D, E, F, G, H, I. This is my 3 by 3 matrix that I must replace each of these elements by the determinant of it reduced 2 by 2. How do we reduce? We reduce by deleting the appropriate row and column where that element lies. Look at A, for example. If I use A, so A is on row 1, column 1. So for A, are replaced by the determinant of EF, HI. That's for A. I do the same for B. B is on row 1, column 2. What 2 by 2 line be left with? So if we do that, then we will find the matrix of minus of that matrix as follows. For element A, I delete row 1, column 1 to be left with the determinant of E, F, G, E, F, H, I. I do for B. I delete B is on row 1, column 2. I'll be left with DF, GI. DF, GI. I replace element C on row 1, column 3. I'll be left with DE, GH. That's for row 1. I do the same for row 2. The first element is D. D is on row 2, column 1. So if I delete row 2, column 1, I'm left with BC, HI. I go to element E. E is on row 2, column 2. So that leaves me with AC, GI. I go to element F. Is on row 2, column 3. Row 2, column 3. That leaves me with AB, GH. Then I do row 3, element G. Element G is on row 3, column 1. Deleting that leaves me with this and that, BC, EF. I go to H. H is in row 3, column 2. Deleting that gives me AC, DF. Then finally, I, row 3, column 3, and that gives me AB, DE. This is what we refer to as the matrix of minus. This is the matrix of minus. Now, assume that this determinant gives me A. This one gives me B. This one gives me C. This one gives me D. This one gives me E. This one gives me for F, G, H, and I. What I've indicated to in green is the determinant. So that we are saying that out of this, you will get the matrix A, B, C, D, E, F, G, H, and I. These are the determinants from this. Then it gives me an opportunity to now define step 3, the matrix of cofactors. The matrix of cofactors. What is a matrix of cofactor? This is a matrix obtained. A matrix obtained from the matrix of minus by applications of the signs that I have given there. Plus, minus, plus, minus, plus, minus, plus, minus, plus. We apply that. which consequently therefore means we are performing operations of signs on the matrix of minus to get the matrix of cofactors. So if that's the case, then the matrix of cofactors will be evaluated by, for first row, it's plus, minus B, then C, minus D, E, minus F, then G, minus H, then I. Observe how we are arriving at this, we are applying this. How are we arriving at this? We are evaluating the determinants of this. Like for A, it's EI minus FH, DI minus FG to give us B. That's what we are saying. Then the second last step, number 4, we define what we refer to as the adjoint matrix. The adjoint. What is an adjoint matrix? This is a transpose of the cofactor matrix. Transpose of cofactor matrix. What did we say a transpose of a matrix is? A transpose of a matrix is that matrix obtained by interchanging the rows and columns of the matrix. So this means that if we transpose the cofactor matrix, then we get the adjoint matrix. The first row, A minus BC, will become the first column, A minus BC. The second row will now become the second column, minus D, E minus F. Then the third row becomes the third column, G minus H, I. This is the transpose. And now finally, number 5, evaluate the inverse as 1 all over the determinant times the adjoint. 1 all over the determinant times the adjoint. I quickly repeat through the steps. Step 1, evaluate the determinants. We have seen even examples on how to get the determinant. If the determinant is 0, then that matrix has no inverse and is called a singular matrix. If the determinant is not equal to 0, proceed to evaluate the matrix of minus. A matrix of minus is that matrix that's obtained by replacing each and every element of the matrix by the determinant of its due reduced 2 by 2. What is this reduced 2 by 2? We delete the relevant row and column where that element lies. If I'm looking at the first element A is in row 1, column 1. If I delete row 1, column 1, I'm left with EF, HI. So the determinant of EF, HI will replace A. I go for B, C, D. For D, I now eliminate row 2, column 1. If I delete row 2, column 1, I'll be left with BC, HI. BC, HI, whose determinant will now replace element D. So suppose for element A, I go determinant as A, element B, B, and so on up to element I with the value I. Then this will be my determinant for the respective element. When I apply the sequence of signs, plus, minus, negative, plus, negative, plus, negative, plus, minus, then what I get is the cofactor matrix. Once I have a cofactor matrix, I transpose that to get the adjoint. Then I can evaluate the inverse as 1 over determinant times adjoint. That gives the inverse of 3 by 3. Example. Example. Find the inverse of the matrix 2, 1, 4, 1, 2, 2, 3, -3, -2. Let that be matrix A. Let us for step 1 get det A. Find determinant of A to check if that matrix is singular or not. Please share the value of your determinants on the chat box. Just use this example all through.
Recording in progress.
I'm in class. I'm in class. Hey. Hey, they are getting different results. -24, -28, -24, negative.
If you are not going to mute your mic and camera, for now we are going to get this class. Paul Muluma. Okay, look. Yes, let me remove them because we instructed them to mute online person. At least do not let me mute.